Right, first of all, I think before we launch straight into looking at impacts, we should really start seeing what we know about embodied impacts. So hands up who thinks they know what embodied impact is in a building. None of you? A couple, okay. And so who thinks that it sounds important even if you don't know what it is? Only a few. All right, everyone, good. I was going to sit down then. Right. Okay, so to explain very quickly what embodied impacts are, the materials or products that go into a building have obviously been manufactured, processed for a long chain of activities. And each of those points in the chain, right from extraction, depicted by these images here, has emissions that are released into the atmosphere, land, water, and so on. There's transport in between each one, and then when it comes to fabrication and processing and assembly, there's more emissions that occur there. And then the products are transported to the site, they're installed, which has impacts again. During the life of the building, there's the need for maintenance, more products have to be put into the building during its life, there's impacts associated with that. And then at the end of the life of the building, all of the products and materials have to be disposed of or recycled somehow. So again, more emissions, more impacts. So it's embodied is the term which is generally used to describe all of that and say it's actually in that material, even though obviously you can't see it. Some typical ones that people look at are obviously carbon and water. And the kind of science or art to some of analysing and measuring this is known as life cycle assessment or life cycle analysis, best perhaps called LCA. And from that you can not only measure, but you can start to assess performance and decide which building is better than another on this basis. So that's largely to do with materials, and that's really where LCA's been for a long time. But now we're moving into an area where buildings can be described as having embodied impact, and it's basically the sum of all of the emissions and so on from the materials which are in the building. So we know what it is, I think, now, but is it actually important? Well, here I've got some pie charts showing the proportion globally of 4 key materials. And you can see that for steel, over half of all steel goes into buildings. For cement, nearly all of it goes into buildings. And for aluminium, it's a quarter. And for plastics, a fifth. So considerable amount of all of the materials we produce under these headings goes into buildings. In terms of CO2, and this is globally, not just the UK, you're looking at 1.8 gigatons of CO2 or 2.8 gigatons of CO2 for cement, which I don't know if you can picture that. I certainly can't, so perhaps we should try and compare it to something else. So here we've got at the top left pie chart is annual global CO2 emissions. It's buildings in terms of operational, so that's energy, water, and heating, cooling, that kind of thing, is the yellow section. That's 32%. 37% is industry globally, and that contains the production of construction materials. And if we break industry down, around half of it is attributed to the 4 main materials we've looked at in the previous slide. And if we apportion each of those according to what goes into buildings rather than other things, then we can work out the proportion of industry emissions which go into buildings. So you've probably already got there at the bottom, we've got a pie chart that shows 13% of all CO2 globally goes into the fabric of buildings, and that compares to 32% of operational. So I think you can see it's quite a considerable amount that we really should be looking at. And as Craig alluded to earlier on, it's only getting more important. the operational impacts are being gradually brought under control with successive legislation like Part L. And this has meant that a slight increase in embodied impacts has occurred because of the need for extra insulation and so on. And the other fact that should be sort of thought about here is that because embodied emissions are all largely up front, so as soon as the building's finished, all the emissions have occurred the year before or the year before that. So they're already up there in the atmosphere doing damage. And when we've only got a limited window to deal with global warming, this is quite significant because operational is obviously eked out over many years of the life of the building. So it's certainly something we should take seriously. And to start to take it seriously, we need tools that will allow us to measure and analyse, and that's where impact came from. So let's have a look at some of the features. Well, in a nutshell, the impact, basically, the method is a case of timesing rates by quantities. So if you've got an amount of CO2 per tonne of cement, and you know you've got 10,000 tonnes of cement, you can work out basically how much CO2 is embodied there and has gone into the atmosphere. So that's putting it very basic, and you can do this for several different indicators, not just CO2, water toxicity, resource depletion, ozone. There's several that can be considered. And the benefit of the use of IES VE or other BIM packages is that you can take quantities off of a 3D model very easily. And this has really been the point at which we've been able to do this, to automate it. Up until now, it would have involved somebody measuring by hand, for example. Very laborious, slow, and expensive. So this is really, now we're able to do this very quickly and effectively. So we've designed the process of using impacts to fit into the workflow that designers would typically do if they're doing BIM. It capitalises on putting information in once and using that information for several things. So if you're telling VE that your walls are made out of so-and-so construction and a roof is made out of something else, you can use that for cost purposes, you can use it for operational energy purposes, and now you can also use it for embodied impacts. And we've kind of split the use of impacts into two separate kind of stages. The first one is using pre-made constructions. So I don't know if you're familiar with the Green Guide to specification, but basically we put all of those specifications into impact. So within a couple of hours you can take a pretty sizable building and apply all of the different specifications very quickly, and you can then try to see how perhaps building shape affects impacts, changing those specifications again very, very quick and easy. So you can, at the beginning of a project, perhaps up to planning, when you're doing scheme design, you can get some pretty good feedback right from the start. But then of course later on you'll get more and more technical information, more detailed information. So the second stage of impacts is to start to refine those constructions. So you'll be progressively moving through the building, changing the pre-made specifications for the ones that you've built up layer by layer. So thicknesses of materials, densities, spacings of studs, service lives, very, very sort of detailed level. So you're moving towards a much more accurate building specific measure of your building. Impact is, unlike predecessors methodologies, it's not an elemental assessment tool where you're just comparing external walls to other external walls in isolation. It's a whole building assessment. You're really looking at results for the whole building. And this is my funky animation. It took hours, this did. So because you're now looking at buildings, not just individual parts of buildings, you can start to really optimize for your site. You can look at how it works with operational, the balance between embodied and operational. You can start to perhaps offset if you've got a particular problematic part of the building. A classic would be the substructure has to be pretty intensive and massive because of the state of the soil, the ground conditions. If you're trying to hit a target, you can offset those emissions somewhere else. So you're really looking at the whole view all the time. The other benefit is that through whole building assessment, the comparison is really the building type and how much of that you're providing. So for example, offices, it would be how many metres of net internal area. So you can avoid the need with elements of like an external wall of, you know, what does that external wall do, what's its performance, and that normally gets boiled down to very basic functions, so things like the U value. So it just avoids and tidies up the need to do any of these things. In terms of LCA credentials with impact, it's not just carbon we're looking at. There are 13 different issues that you can use with impact. It's the same 13 issues we've been using at the BRE for some time. So you can either look at all of those values individually and try and compare them when you change the design, or if you can't store that many numbers in your head at once, we have BRE Eco Points, which is a weighted summary of all of those issues. So it's kind of an amalgamation of those, which makes things a bit easier.
Sorry, what's LCA?
Life cycle assessment or analysis. I've mentioned already the Green Guide to specification is in impact, so that those are familiar, and also our certified, which are sort of proprietary products that we assess. Those are in there as specifications and as separate individual materials too. We are also able to break the results down according to life stages. So the product stage is basically the emissions that have been caused by the products up to the point where they've got to what's called the factory gate. Then we have transport, installation, in use, which is refurbishment really, and then end of life. So you can look at a huge array of numbers if you want to. These life stages and indicators are designed to be compatible with the recent CEN TC 350 standards, which are European-wide attempts to unify LCA practice. So we're kind of ready for CEN in that way. The data that goes into impacts is quite specific to different regions. Some regions can be quite big, but the data we have from the BRE is largely UK based. However, you can use it in other regions if there's no alternative, but obviously it'll affect the kind of reliability. But we have designed it so that you can bring in different data from different regions. Canada's got their own database, France, Germany, Switzerland, many of the European countries have, Australia. So it's designed so you can, if you put your data into that format, you can bring it into impact and use it in those countries. We're also ready to, when CEN EPD data, a comprehensive database is made available, we can bring that in too. And lastly on that slide, validation. So we've got several tests that are carried out on models to make sure that the accuracy there and it's reliable and rigorous. We've heard something about cost optimization earlier on, and impact, pretty much half of the tool on the project was about looking at life cycle costing. So this is not just the upfront cost of a building, which is capital cost, it's how much it costs to run, maintain it over a given period, usually 20 or 25 years. So impacts, through putting the specifications into the model, will calculate that for you, so you can start to optimise cost against embodied emissions. The study period is flexible from 0 to 80 years. That's the life, or the length of study you're doing for the building. Different so activities require different lengths of study, so that's totally flexible. And we're using the NRM system mentioned earlier on as well for categorising the elements and items in the building, so that's makes it compatible with quantity surveying practice. With BREEAM, which I'm sure you're all familiar with, from the offset, impact has been, although it's a standalone tool, the outputs are suitable for use in BREEAM. In the next revision that's coming out, there will be the opportunity to earn 2 exemplary credits, which means it's like a reward for having undertaken a certain activity, in this case using impact. However, there'll be minimum requirements for how accurate the model is, that it contains all of the elements that we say it needs to contain for it to be comprehensive enough. And we also will be looking for a statement about how impact has improved performance since you've been using it, of the building's embodied impacts. I've mentioned the international situation, so that's kind of in development at the moment. But the most important point here about this sort of 2-year stage of exemplary credits is that we can start to gather highly important data about real buildings, so that we can build, or we can put together benchmarks of performance. So if we say have 200 office buildings, we can look at the impacts, we can normalise that to a square metre of net internal area and work out an average and say, right, that's the benchmark, that's the average performance. So if you're 10% better than that or 20% better than that, you'll get X amount of credits. So that's where we want to get to in a couple of years when our data sample is robust enough. So just to finish off, the project sort of breaks down like this. We're very close to launching Impact, still down for October, I think. So that's in VE. Following that, there'll be a tool, a plug-in to other BIM software coming up shortly. But then phase 2, which we're working on now, is where we're producing a written specification that contains all the formulas and rules required to make a tool impact compliant. And that's written really for software developers to make their own impact compliant part of their software, if you like. And this means that the impact compliant tools will be giving the same results. There'll be comparability. It's really the kind of standard we're looking for in the industry for being able to compare building performance. So that's the future. And that's it. Thanks very much.
Whilst everybody's been very professional and knows exactly what they're talking about straight away, I do have a little script because I do tend to forget what I'm talking about halfway through the presentation. Please don't let that detract from what I'm about to say though. Following on from Daniel's little hands up earlier, I'd just like to see who actually knows what VRV equipment is in the room. Thank God for that. That's brilliant. Okay, excellent. Everything that you see here today, not just from myself but from everybody else, has one effective reason behind it. And that is because of this. Now, everything that you see in here today is to try and improve what we have here for the future, so that we don't let our children down, so that they don't turn around in 20, 30, 40, 100 years' time and say, even though they knew that we were causing a problem for the planet, they didn't do anything about it. Okay, that's it, don't worry, there's no big, long, saving the world speech to follow from this point, okay? But it is important to remind ourselves that what we do has a higher purpose. It's not just to meet regulations, to pass building control consent. There is a higher purpose behind what we're doing. And the IES software, along with ourselves and a lot of other people involved in these projects, you know, are really quite passionate about what we do and the reasons behind it. To give you an idea of why we started talking to IES and how the development came about in the first place, we were talking a few years ago about how brilliantly efficient VRV systems are. You know, if the outdoor temperature was exactly 13.2 degrees for the entire year, and you had a system that was in 50% cooling and 50% heating, then you could achieve an efficiency of 10. Brilliant. But what good's that in the real world? Yeah? When's it ever 13.2 degrees outside for the whole year? It's not. Okay, so to make this realistic and to find a way of actually finding out how efficient our equipment can actually be, we needed to perform some form of simulation on it. Now, we didn't just speak to IES, we spoke to several companies. IES themselves were the only company that asked us where our data came from and asked us to justify the figures. Now that, from our point of view, meant that IES matched our own ambitions to be credible, transparent, and open and honest. The development of this tool by itself is really about, from Daikin's point of view, we're sticking our head above the parapet now. We're saying, look, if you put our systems into a building and you model it within this type of software, this is going to be the efficiency that you actually get out of these systems, or the likeliest efficiency. In some cases, this means that you can get exceptional performance out of the systems. And I'm going to give you a few demonstrations about how you can achieve this and some of the things that we've also discovered whilst actually using this tool. The tool itself took us 2 years to develop. The initial development was supposed to take 6 months, and that's not anything to do with it being difficult. It just took a long time in order to make sure that everything worked the way it was supposed to. Okay, so I've already gone far too far off the script now to recover. To get above a certain number of floors, in the mornings and the evenings, the stack effect, or the effect of air travelling, warm air moving through the building, means that you can still require heating at the bottom of a building while the top floors require cooling. So you can recover heat between both of those areas, and that effect seems to last a lot longer than the east-west accountability of the systems. Okay, some other discoveries that we've had. Leaving the systems on. You turn a system off, what happens to the temperature? It changes. If you leave the system on, you maintain a temperature within the space. This is just some output details here from design that we looked at a server room. Again, we were looking for heat recovery efficiency within the space. And you can see the spikes of the peak loads when you turn the system on, and how they affect the performance of the VRV system. So you can see there, again, we've got increases, but may not be the best way to do it. If you then look at leaving the system on 24 hours a day, 7 days a week, you can see there directly from the graph that you've lost all the peaks. Not only have you lost all the peaks, but from a heating point of view, you're actually heating the space and maintaining the space temperature throughout the night, probably using cheaper electricity. But also the efficiencies of the system go up. Now this is all done on the same model. Both of those two examples that I've shown you there gave an increase of nearly 13 megawatts over the entire year. So you've got significant savings that you can find with this tool. Not only savings in regards to carbon, but obviously the related costs as well, the performance of the system. But the main reason anybody has these systems in the first place is for comfort. using this type of system in this type of scenario, people will walk into an already conditioned space. And the fact that that space is already conditioned and has used much less primary energy use in the first place is testament to the fact of what we can now do with this software. By embedding VRV systems within IES, we can realistically see now how best to engineer the systems. Going back to the vertical efficiencies and the horizontal efficiencies, this tool is so important for us as a company because it can drive our product development. One of the things that's going to happen because of this discovery with the vertical efficiencies is in our next generation of VRV equipment, we're going to increase the distance that you can span your fan coils from vertically. At the moment, you can probably cover 4 or 5 floors with the limitations at the moment, but it's likely to go up to around 10 floors. So you can really maximise the heat recovery effect, giving you great performance from the HVAC systems within your building. Now, just to close, I'd just like to mention one thing. This development that we've done with IES by incorporating VRV into the software is not a short-term thing. In fact, the primary reason that we did this was for some equipment that you don't know about yet. In fact, very few people know about yet. But it's something that's coming very soon. VRV4 should be here within the next 3 or 4 months. But it's an evolutionary process. It's not going to start off being, wow, this is a brilliant system with all singing, all dancing, here we go, with some incredible amount of fanfare from us. It's going to evolve over time. The primary reason that we created this development within IES is for VRV4. There's some significant developments and changes within what you consider VRV to be in the future. We've already started putting some of these features into VE, into the Daikin plugin, and that's being developed at the moment. And we expect to see increases. Well, I have to stop myself there because I'll get shot by my boss if I start talking about it now. But expect to see some very, very interesting developments from Daikin VRV in the next few months. Thank you very much for taking the time to listen to me.
Hi, so my name's Alex Brewer. I'm a technical consultant for Monodraught, and I'm here to talk to you about the Windcatcher Performance Components module, which is a new feature which we've developed with IES over the last couple of years. It got launched earlier in the year, and we basically now have a library, if you want, a catalogue of Monodraught's Windcatcher systems available within the IES VE as standard as part of the new feature. Now, these are predefined, what we're calling performance components. So each element of a single Windcatcher object has the thermal templates, the macroflow opening profiles, the construction profiles, everything predefined, and the user can simply drag and drop it onto a model to then run a simulation to look at the feasibility of natural ventilation. So just to give you a quick introduction to Monodraught, we have 3 key market areas that we focus on. We've got natural daylight with our sunpipe natural daylight systems, natural ventilation, where we have 2 categories of our Windcatcher systems, being the Solar Boost and the Windcatcher, which fall into the X-Air and the Classic categories. Now, these are the systems which we currently have in the Performance Components module, so this is what I'm going to be demoing to you a little bit later on. But we also have our natural cooling system, which we call our cool phase, low energy cooling and ventilation system. It utilises a phase change material, what we call a thermal battery, where we can store and release the latent heat from that thermal battery to actively cool a space. Now, at the moment, as I said, we currently just have the Windcatchers in operation within this Performance Components module, but we are now working very closely with IES to develop a Performance Components feature for our sun pipes, but also for the cool phase. So just to give you a quick overview of a Windcatcher and how it works. I don't wish to patronise you here. I know these systems are very simple in the way that they operate. So we have a terminal unit which is split into 4 quadrants, which is situated on the roof. The idea being whichever way in which the prevailing wind is incident on that roof terminal, at least 1 or 2 of the quadrants of the windcatcher will be exposed to the wind. The louvered faces capture that wind and they pass the air down into the room below. Now the quadrants that are downwind of that prevailing wind experience a negative pressure region as a result of the flow separation around the unit, meaning that the stale warm air that's built up inside the room which the unit is serving is naturally drawn up and out and released, so you get a continuous air change rate. Now the reason I've shown this to you now is because we're actually going to, when I do a quick live demo of the new feature, we can actually see the way that IES mimics this performance through the bulk airflow analysis. And that's just a quick image of our systems in an actual live installation. So, why do we use IES? We're a manufacturer, you know, in most basic terms, but we offer a very comprehensive design service. We've been using IES as our primary design tool now for the last couple of years, and there's a number of different benefiting factors. We've got the fact, you know, there's the diversity in output data which we can analyse in accordance with the use of our systems, but it's also the fact that we're using recognised weather data, so whether it's CIBSE accredited weather files, your TSY, your DSYs or your IWEC files, we're using annual simulations, so we can not only just look at the a steady state scenario under which our systems perform, but we can actually look at how they interact with the building over the course of the year, not just during summertime operation, but during wintertime operation. And we're using certified calculation methods. Basically, we feel that if we present our results to you in IES, then you will trust the results that program is outputting, which therefore puts, you know, you will then have faith in our systems and how they'll operate in reality. So this is all fair and well. We've been doing this design service for a while now. You know, we work very closely with the consultants on our design consultation to really optimise the design of natural ventilation within their buildings. But more and more, we were getting feedback from them saying, look, we want to be able to carry out this design work ourselves. And tutoring guys like yourselves on how to model our systems in the IES is quite hard. To model these systems from scratch is quite a painstakingly laborious process. It takes a lot of time, and if you don't have a complete understanding of how to do it, then it'll take a certain amount of time. So what we've done is created this performance components tool, which basically eliminates that, the time aspect of it. So it's a very quick and efficient means of modelling natural ventilation systems. So this is what we came up with. It's predefined performance component versions of our systems that are available from this catalogue within the VE. Now this feature is available as standard within the latest version of IES. So the VE 2012 that got launched earlier this year, our systems are there. There's no additional plugin as such. All you have to do is simply select the library, decide which component you wish to import, and place it within your model. So Monodraught systems can simply be dragged and dropped onto a building user model, and every performance defining factor is predefined. This is one of the things that I really push home about this feature, is the fact that our invent control strategy is already there. The thermal templates are there, the construction templates are there. Every aspect of that system with regards to that component itself is predefined. So if the rest of your model is set up, be that the thermal templates, the construction templates of your building, then once you've placed that system, it's ready to simulate. Quantifying the performance. We were very aware of the fact that we had to really be sure that the way in which these systems perform in the VE related to how they perform in reality. So we have done a lot of CFD testing. We've got a lot of in-house expertise in CFD modelling. We've done pressure testing. We actually have a test rig back in the office, where we can generate a controlled pressure differential through our systems to understand the pressure, the static pressure difference. And we also do wind tunnel testing and further CFD modelling to quantify how the systems perform with relation to the discharge coefficient when an actual flow of air is incident on the terminal. And all of these figures have been quantified into that single discharge coefficient within the system so that they perform accurately in the VE. So here we have a generic 3-storey office block, and I'm going to take one of the top floor areas and basically just see if I can model a natural ventilation strategy, look at the feasibility for natural ventilation within that area. So the first thing I need to do is access the catalogue, which is available from this Add Components from Library icon, which is a new icon on the interface. So if I click on this Add Components from Library, and here we have the Monodraught Windcatcher catalogue, if you want, the library of our systems. So all of our systems are listed down here. We've got rectangular, square, classics, the heritage systems, and all the corresponding sizes which are available. Now, all you have to do is simply select the system which you're interested in using. You can then, there's then some basic information on what's included within the system, the colours that are available, links to an MBS specification. We have a product data sheet where all the technical information is there. So once you've decided that that's the system that you feel is correct for this building, simply click Import Check Components, close that window, and that system is now available within my model for me to use within my building. So I'm going to say that I want to model my system serving this top floor office area here. Now to do that, I have to duct the system through this roof zone, so which means I have to assign the system to the model at roof level. So I simply have to go down to zone level, change from surface to component, and here is our Windcatcher XAir 170 natural ventilation system, which I just imported from the library, so this is where it's readily available. Now all I need to do is just change the plane height and the duct length. Because I've been doing this a number of times, I know exactly what that needs to be. I can then use this place component icon, which is a new tool, a new icon to the VE. I can place that system within my roof, and if I just look at the front view here, I can see that it's ducting all the way down through that roof zone, so it's sitting flush with the ceiling of the zone below. If I then select that component and click on this new icon here, Finalize Component, that subtracts the geometry of the model that intersects with the component, and the component itself then becomes part of the geometry of the model. So we can see, go on to axonometric view there, we can see the area that's been subtracted, and this Windcatcher here now actually has formed part of the model, so it's its own zone in its own right. So if I just fly up over here, we can see we have the Windcatcher, which has everything predefined. So we've got the construction templates, the macro opening profiles, the textures there, so we can visualize the tool. Now, what I'm going to do here is just jump onto a previous model, which I carried out earlier, where basically what I've done is repeated that same step. So now for the complete top floor office area here, I've repeated the step that I just showed you 5 additional times, so I've got 5 systems serving that total area. And I've run a basic simulation. So if I just go into Vista, we can just look at, for a start, let's say the air temperatures within the space. We're dealing with an office in this particular aspect, so I know that the overheating criteria for that space is no more than 1% of the occupied hours over 28 degrees, and no more than a maximum temperature of 32 degrees C. So if I just look at the graph here, we can see that we're not exceeding 32 degrees C. And if I have a look at my range of hours that are over 28, you can see there 0.9%, so we're within those thermal comfort boundaries. And I should reiterate here that I have actually purposely made this a very heat gain intensive space just to show the potential for our natural ventilation strategy. So we've got 20 watts per metre squared equipment heat gains, 1 person per 10 metre squared occupancy, 12 watts per metre squared lighting. So these are very heat gain intensive spaces, yet we're still getting that natural ventilation compliance. Now, I can also look at elements like the room CO2 concentration. So air quality is often something that people question with these sorts of systems. You can see here I've got my CO2 concentration without the air, and we're not exceeding 950 ppm over the course of that annual simulation. So we've got sufficient air quality within that space as a result of the installation of those systems. Now there's various other elements that we can look to explore, but what I'm going to do now is just show you in Vista Pro quickly a bit of bulk airflow analysis, which relates back to the explanation of the Windcatcher's operation, which I spoke about before. Here, if I just click on System. So what I've done is I've just gone down to zone level here, so we're focusing on the 4 quadrants of that Windcatcher, which are entering the zone in which the Windcatchers are serving. So if I just look at the bulk airflow analysis here, I've got a windrows, which at a particular point in time, if I just scan through to the middle of the day and zoom in, let's have a look. Right, so we've got the wind which is coming from a south direction. So if I now just zoom in on this model here, we can see that the quadrant which is facing that southerly direction, which we can see is over there, is exposed to the wind, therefore that is doing the supply air to the room, indicated by the blue arrow. And the quadrants that are downwind are in that negative pressure region as a result of the flow separation around the Windcatcher terminal, are therefore doing extract. So we've got a complete supply and extract circulation of air to the room, which gives us real confidence in the way that IES is actually replicating the performance of our systems in reality. So just to summarise, key points about this feature: decreased modelling time for natural ventilation strategies for one. Just to give you an idea of how long this would typically take without this feature, for an experienced person that's used to modelling natural ventilation systems, anywhere up to a couple of hours. For someone that doesn't really know what they're doing, you could be looking at almost a day's worth of work for modelling a complete building. We've rapidly decreased that time now. For someone who was new to the software, to do what I've just done and carry out that simulation would probably take 20 minutes to half an hour, and that's just to look at the feasibility of these systems. Increased accuracy. There's no guesswork with the figures that determine the performance of these systems here, because we've predefined everything and we've experimentally validated the figures that are assigned to these performance-related factors. Assess the energy saving potential for natural ventilation systems compared with conventional HVAC schemes. So, you know, mechanical ventilation is used very widely, yet people wouldn't always consider that natural ventilation may be a possibility. And the energy saving potential is huge. It can dramatically reduce the carbon footprint of your building. So if we were to look at modelling the energy loads associated with a natural ventilation scheme, or the capital cost, for instance, the only initial capital cost that goes hand in hand with a Windcatcher system is the initial expenditure. There's no actual running costs from that point onwards. So the energy loads are negligible as well. You've got a slight bit of actuation of the dampers, but that's all there is. So they're a fantastic way of reducing the carbon footprint of a building. And finally, architectural visualization. There's some great new visualization tools, the new model viewer in the VE, and all the textures are predefined within the performance components module, so architects can really get a feel for how these systems will interact with the form of a building, and they can assess the aesthetics and so on and so forth. So that's it. Thank you very much for listening.